Hello everyone. So we are on page 37. Okay. So we're talking about separation of solutions, mixture chromatography, and then solubility principles. And so we're actually starting with these solubility principles. Okay. So this is the 3.10 here. And the big rule when it comes to solubility is that likes dissolve likes. Okay? So what I mean by this is that if one molecule is similar to another molecule, then they will have IMF attractions between them, and they're usually stronger than the attractions that occur between different kinds of molecules, like polar versus non-polar. Okay? And so when we have those stronger attractions, then we're able to pull items apart, and that's how we would dissolve. So here's the three things I want you to think about. We're going to be talking about polar molecules. We are going to be talking about ionic compounds. Okay, ionically bonded things. And then we're talking about nonpolar molecules. Now, the reason why I put them in this order is because polar molecules and ionic compounds are more similar. These are similar. Let's talk about those similarities. First off, if I have an ionic compound like sodium chloride, here's a model that represents this, okay? So I have my metal and my non-metal. So for these ionic compounds like sodium chloride, metals lose electrons, non-metals gain electrons. We talked about this in the last video, and they form ions. So the chlorine is actually going to take away an electron from the sodium. So how this would look is like sodium has 1 valence electron. Chlorine has 7 valence electrons. Okay. And chlorine is more electronegative. It has a way higher capacity to grab electrons and steal them from other atoms. And so like what this turns into is sodium plus, because it lost an electron, and chlorine minus, because it gained an electron. And then all of a sudden there's a positive thing and a negative thing, and there's an attraction between them. That's the ionic bond. It's that attraction. But what I want to show you here is that in ionic compounds, we have positive cations and we have negative, I wrote it on the outside, and we have negative anions. Okay? So these positives and these negative things. Now, this is very similar to polar molecules that have partially positive areas and partially negative areas. Back to water, because it is definitely our most utilized and talked about on the AP Chem test, polar molecule. So with polar molecules, we get areas, regions of the molecule that are more negative and regions of the molecule that are more positive. They are not fully positive and fully negative because we don't completely lose and completely gain electrons. But these shared electrons right here, they spend more time with oxygen than they do with hydrogen because oxygen is more electronegative. And so that makes this oxygen partially negative and the hydrogens partially positive. These lone pairs contribute to that negativity as well. And so then we have this region of the molecule that is definitely negative. And that's where they are similar. In ionic compounds, there are positive cations and negative anions. In polar molecules, we have positive dipoles and negative dipoles. Okay? And we can get attractions between those, and we've seen this. So here's a model of water. Here's our ionic compound. Now, we said that the hydrogens are the positive region And remember how cations lose electrons so they become smaller? And look, it's trying to push it away. It doesn't want to connect. But what about the oxygen? The oxygen is a negative region. Oh, that has an attraction to that cation, right? Where the positive side, the hydrogens, is attracted to the negative anion. And we can get enough of these water molecules to surround these ions, and all of these water molecules together are strong enough to pull apart the ions and dissolve it, right? So that we have free-floating ions inside of water. Okay? So, likes dissolve likes. Ionic compounds are dissolved by polar molecules. Okay, so let's talk solute and solvent. Okay, remember, solvent, that is usually, almost always the liquid, and the solute is the thing that we're putting in there, okay? Solute. Okay, let's draw a little table, actually. Okay, whoop. And then okay, this is what I got right now. Solvent, solute, miscible. Okay, so miscible means that it dissolves. And so was it miscible? Yes. Or was it not miscible? No. So if we have a polar molecule for our solvent, like water, so this would be really common, and a polar solute, that would be like sugar. This is miscible. This does dissolve because likes dissolve likes. Okay, what if we have a polar solvent and an ionic solute? These are similar enough, we just discussed, that they are miscible. It does dissolve. Okay. Then we have, what if we have polar solvent and a non-polar solute? Oh, not similar enough. Okay, does not dissolve. Now let's switch over to non-polar. So what if we have non-polar solute, or sorry, solvent, non-polar solvent? We already know from the previous one, because these could absolutely just switch spots. So we already know from the previous one that if it's a non-polar solvent and a polar solute, then it's not going to be miscible. But if it's non-polar and non-polar, those ones are similar, so yes, they are miscible. They do dissolve. Okay. And then last one here, non-polar and ionic. Not similar enough, does not dissolve. Okay, so this is going to be really dependent on if molecules are polar or non-polar. Where we practice that, we spend a lot of time identifying if a molecule is polar or non-polar based on symmetry and asymmetry, or if it's an ionic compound, we're looking for metals and non-metals. Okay. Okay, so let's do a couple of these practice problems. We're going to skip this first one. We're going to do this one together in class and jump down here. Of the following organic compounds, which is the least soluble in water? Okay, so water, H2O, polar molecule. And then let's see what we got going on here. Oh, this was a tricky one because look, it looks like it was nonpolar, a hydrocarbon, but it's not. It's got an oxygen in there. It's got a little hydroxyl group at the end. Oh, so then that makes this a polar molecule. Hexane, oh, hydrocarbon. Only hydrogen and carbon. And so that would be London dispersion. It would be nonpolar. Glucose. Okay, so glucose, again, look, there's oxygen in there. So this is not a hydrocarbon. I think it's a very high likelihood that it's a polar molecule. And then we definitely know acetic acid is because look, hydroxyl group at the end, OH, so this is polar. And it's the least soluble. Oh, so likes dissolve likes. So dislikes do not dissolve. So if this is polar, we want to pick the one that is non-polar. Hexane is the least soluble in water. Okay, now, next one. Which of the following substances has the greatest solubility in C5H12? Oh, hydrocarbon. Only hydrogen and carbon, so that's a non-polar molecule. Now, we may need to draw our Lewis dot structures on each of these to see, because we have silicon, oxygen. There's my skeleton structure. Oxygens have 6 valence electrons, so I'm going to start right there. Silicon has 4 valence electrons, so I'm going to start right here. But free radicals, we don't like free radicals, so I'm going to take this electron and one of them from silicon and turn that into a double bond. I'm going to do the same thing on the other side. So what we have is oxygen double bonded. Oh, that's symmetrical. So that's nonpolar. So this is nonpolar. This is also nonpolar. Greatest solubility. Okay. So let's think about that. Greatest solubility, and this one's nonpolar. So maybe that could be a potential answer. Oh, water, we already know is polar. Oh, this was supposed to be a parentheses right there. CCl4 is also nonpolar, though. CCl4, okay? So that's what carbon with our chlorines. Okay, so that one's also nonpolar. And then NH3, this one's polar. We can draw this Lewis dot structure. It's got a lone pair on it. That's where our asymmetry comes from, so this is polar. Okay, so we've narrowed it down to A and C. And I just want to show you, C5H12 is a rather large molecule. And so its London dispersions are strong. And so we're looking for, if we have 2 that are nonpolar, let's go with the larger one because its London dispersions are going to be strong, just like the C5H12. Okay? So silicon and carbon are somewhat similar. Oxygen, chlorine. Maybe let's just do a quick molar mass on this. So silicon. Oh, well, it's going to be chlorine. This one's going to be so much bigger. We don't need to. Because look, there's only 2 oxygens, and there's 4 chlorines. So since that one is larger, it's got more polarizable electrons, its London dispersion would be stronger. So that is the one with the greatest solubility. Alrighty, nice. Separation of solutions. So now we are going back to 3.9. Okay, so that was 3.10. Now we're talking about 3.9. There are 2 main ways that we separate solutions. Okay, we've got a solution and we need to separate those solutions. Chromatography is a main way we do this. Distillation is the other ones, though. Okay, so here, and factors affecting solubility, sorry, that's actually later. So we're just focusing on these two, chromatography and distillation. We've talked about chromatography, but here's a little reminder for us. Let's start with paper chromatography. Okay, so imagine with me that this is our strip of paper, and we've like zoomed into it so much, and we are going to be depositing a sample at the bottom of this paper here, okay? And it contains two things inside of this solution that we're setting down there. But we're really zoomed in so we can actually see the different parts that are in here. But guess what? Macro view, these things are way too small. We wouldn't be able to tell that there's just two things in there. And now we're going to have water that we are going to move through this paper, okay? The stationary phase, the thing that is not moving, and in this case it is the paper. In this case it is the paper. It is the opposite of polarity to the mobile phase. So we have a stationary phase that's not moving. We have a mobile phase that is moving. And in this example that I'm showing you, water is polar, and then the stationary phase is non-polar. So as water travels through this paper, it's grabbing onto items that it's similar to. And so now we can see that we were able to separate this solution because part of the solution was polar or ionic, but likely polar, like the water. And part of the solution was nonpolar, like the paper. So likes dissolve likes. Likes grab onto likes. So if the thing that is moving is polar, it's going to grab on to other polar things. Okay? If the thing that is stationary is nonpolar, then it's going to hold on to nonpolar things and keep them where they're at. And we were able to separate this. Okay, so what if I put a little sample right here, okay, and that sample, I then set this in water right here at the end, and the water travels up the paper, okay? This is called where you can like see the water has traveled. The edge of that traveling water is called the solvent front. And it took this dot and it separated it into three distinct colors maybe. We got like a blue, a red, and a green. I don't know. So it separated them. Okay, so it's like I took this like brown ink or something and it separated a blue, a red, and a green. We can gain some really interesting information from this. First, if it was water that traveled through here, then whatever traveled the most is the most polar, and whatever traveled the least is the least polar. Some traveling will happen because we know like London dispersion, like there are attractions there, but the one that is polar will travel the most. Okay, so based on this, we could say B is the most polar, then it's A, and the least polar is C. Now, what if the mobile phase was non-polar? And that's actually this. Okay, so I give you an example where water, the mobile phase, was polar. What if the mobile phase is non-polar? This liquid that I'm going to have travel through here is no longer water, it's something else, and it's non-polar. Likes dissolve likes. Likes hold on to likes. So if the liquid that was traveling was nonpolar, then whatever traveled the most is similar to that. It's nonpolar or the least polar. And the one that traveled the least is the most polar. Okay? Okay, so mobile phase, stationary phase. The mobile phase is the one that is traveling. The stationary phase is the one that is not. Whatever part of the sample travels the most, then it's the most similar to the mobile phase. Whatever part of the sample traveled the least, then it is more similar to the stationary phase. If we need to separate polar and nonpolar things in much bigger quantities than just putting a little dot on paper, then we're going to use something called column chromatography. Okay, so in column chromatography, we get like a burette, okay? So it's got like an opening down here that liquid can travel through it, okay? And we add a solid phase in there. So we put some solid stuff in there, okay? And sometimes the solid stuff is nonpolar. And then the liquid that we pour into here is polar. And sometimes we flip-flop those, okay? So if I want to separate a much greater portion of my sample, I'm going to put the solid stuff in there that's not going to move. And let's say for this one it's nonpolar. Then I'm going to add my sample there on the top. And then I'm going to take my liquid and pour it through it. In this case, it's going to be polar. Maybe it's water. And so then what if it takes a sample and it separates it, and we see that we get like a chunk that's right here and a chunk that's down there. As it traveled through, it pulled it here and it pulled it there, okay? This original sample was the combination of both of these things, right? Okay, so it must mean that this part of the solution is closer to, it's less polar, or it's closer to being nonpolar. And then the one that traveled the most, that's going to be the most polar. Okay, good. The other separation technique that works well for polar versus nonpolar things, really it's strength of IMF things. We have distillation, this is such a fancy apparatus. We can simply boil something off, boil it at a different temperature, and that's also distillation. But if we then want to catch it, this is how you would condense it back to a liquid, okay? So if I have two things that have different IMF strengths, that would mean that they have different boiling points, okay? So I'm going to take ethane, C2H6, and I'm going to say that it's got, let's just look it up really quick. Boiling point of C2H6. Okay, the boiling point, it's low. We got negative 88.5 degrees Celsius, but at least that's what the new like Google AI is telling me. Now, oh, well, let's just do water. That's easy enough. And I got this actually we shouldn't do because it wouldn't mix. So C2H6, and we're going to mix that with something much bigger. C4H 79 C10. Okay, let me look that up. C4H10. Okay, so everyone, the boiling point of C2H6 was negative 88.5 degrees Celsius. Now make a prediction right now. Is the boiling point of C4H10, is it going to be higher or lower than that? Both of them are hydrocarbons, so they're both nonpolar. They both only experience London dispersion, but the larger the molecule is, the stronger the London dispersion. And just a reminder, the stronger the IMF, the higher the boiling point. They're directly proportional. So since this molecule is bigger, it has a stronger London dispersion, so it has a higher boiling point. These are negatives, so don't freak out. Like, isn't 88 bigger than 11? Yeah, but negative 88 is lower than negative 11. Okay, so what if I mix these two things together and now I want to separate them? What would I need to do? Let's get this on this mixture onto a hot plate, okay, or an apparatus like this, like they're both in there, and then I'm going to start cranking up that temperature, and I need to be careful though, because a hot plate may not even be a good idea. I need these temperatures. I need to find a temperature that is in between these temperatures, right? Because if we are at like negative 20, then what would happen here is that this one would be boiled off. This would leave. It would become vapor. But this one would stay. This one would stay as a liquid. Sorry, the negatives are throwing me off, so I'm trying to make sure I'm saying this correctly. So, lower, negative 20. I said them backwards, huh? Lower temp. Higher temp. Okay, and so the boiling point is lower, the boiling point is higher, negative 20, and so then this one would have vaporized. Yeah, that one would have vaporized, and this one would have stayed a liquid in there, and now we've separated them. Okay. Oh, this is solubility. Okay. So, if we have two substances that have different boiling points, distillation is a great way of separating them. Okay. If we have water that boils at 100 degrees Celsius, okay, and we combine that with boiling point. Let's see if we get a good boiling point on this one. 42. No, it's giving me propane instead of propanol. Sorry guys, I'm trying to find a good example for you. Oh, this one works. Okay. If I have this and I have 1 propanol and it boils at 97 degrees Celsius, this would, I love this example because then I'm going, oh, I probably should not use distillation on this because look at how similar they are in temperature. But then if we get something else that has like a lower boiling point, we'll just say 42. Now this would be a great way. Distillation would separate these really well. We want to pick a temperature that's in between these two. And so then the water hasn't boiled yet, so it stays a liquid in there, but the other item has boiled, so then it leaves as a vapor, and we're able to separate that. Okay, awesome. let's do this example and kind of talk about this in class as well. And so next time we're going to go over this problem. We're going to go over this. We're going to do a few practices, and then we are headed into the lab. Okay, see you guys all in class.